Understand today, Professor Siphon will tell us a bit more about 3D printing and how to design web art. So with no further ado, Professor Siphon, please join me in welcome.
Thank you. So first I'd like to thank the organizers for the invitation to speak, and thanks to Siu Wing for the very kind introduction. I have a day job that involves triangulations of three manifolds, and I also do these 3D printed mathematical art and visualization projects. And I'll be speaking in the triangulations workshop later on in the conference, but today I'm going to speak about mathematical art. So let me first tell you a little bit about the technology of 3D printing. How does it work? There's a few different related technologies that all come under that heading of 3D printing. So the one that maybe you've, if you have a 3D printer at your university, or the consumer models, all are these fused deposition modeling style. And so what this means is you have a print head, a nozzle which is heated up, and you're squirting through melted plastic. And then you have a bed here, which you're squeezing this melted goo onto, and you're building a structure. And so the point is that you need, somewhere in this, there has to be 3 degrees of freedom. So either the print bed sort of moves in 3 dimensions, or the nozzle moves, and that allows you to very precisely choose where you're going to squirt your next bit of plastic. And this is there's other ways to do this. This is a sort of an interesting alternative way to do this. What's going on here, there's these 3 vertical rods, and there's motors that allow these parts here to move up to any height that you want on those 3 vertical rods. And there's an interesting little math problem here. If you want to put your nozzle at a particular point in space, to which height do you have to raise these 3 motors to achieve that? So this is maybe the most common kind that people see around. There's some sort of technical problems with what this lets you do. One of the issues is to do with overhangs. So if you're trying to build an arch, or even worse, sort of an arch with a dip at the top, and you're building your object up layer by layer, then when you get to the layer which has the start of this dip, you can't just put a blob of plastic there because it will fall onto the ground. And so you have to build scaffolding up underneath it, and then you can start building the actual object underneath the scaffolding, and then the scaffolding needs to be removed by hand later on. And this is problematic if you have very complicated internal structures, for instance. Another well-used technology, this is called stereolithography. So here the idea is that you have a bath of a liquid resin, and you're building your object layer by layer on the top surface of this liquid resin. And a laser comes along and solidifies, activates the resin, and solidifies it sort of voxel by voxel. And then when you've done this layer, this piston moves down by one layer, whatever your layer thickness is, and then you go another one, you go and zap over everything again. And in this case, you don't need so much scaffolding. What do you need? You need sort of, if you're building something, say this first piece on this dented arch, then you just need a very thin line of scaffolding up to the point which you're going to zap with the laser, just so that it doesn't float away, so that it stays put as you're continuing. But then these smaller pieces of scaffolding you can more easily get rid of. And then this is the last one that I'm going to talk about, called selective laser melting, or sometimes selective laser sintering. All of these objects that I have here were produced using selective laser melting. So here what happens is you've got this sort of vat full of plastic dust, and it's heated up just below the melting point of the plastic, and a laser comes along and solidifies it on the top layer where it wants to be solid, and then this roller pushes over another layer of plastic dust, and then you repeat and you repeat. And the advantage here is that any of your things that you're building are supported in the vat of unused material. And so there's really a huge amount of freedom in the design of what you're allowed to do. You don't need to produce scaffolding. You just need to deal with sort of minimum thicknesses and so on. And then you can get this thing printed, and then at the end you have this tank full of dust that you just vacuum out all of the excess dust, and you have your object. So these are the technologies involved. From a mathematical point of view, there's a number of issues. Perhaps the first one to start with is the problem of thickening. So very often, the mathematical objects that you're interested in are one-dimensional or two-dimensional, and they don't intrinsically have a volume to them. And of course, you need a volume in order to tell the computer what to make out of plastic and what to leave alone. So here's a sort of standard example. This is a trefoil knot, and you need to thicken it up somehow. So this is just this is not a difficult process to do in this case. So this is just taking a radius tube around that curve. And then there's a next stage. This is a little hard to see. So I should mention this modeling program that I use is called Rhinoceros. It's a NURBS modeling system. So if you're not familiar with NURBS, it's a little like Bezier curves, but generalized to 2 dimensions. But the thing that you need to give the printer is a mesh. So in this case, this is a quadrangulated mesh. There are all of these quadrangles here. And in general, you can have quadrangles and triangles, and you need to give this sort of object to the computer. And then you produce the actual object. So here's another example. So this is a little hard to tell what this is. This is the molecular. This is a small chunk of the molecular structure of diamond, and thicken it up and make it out of steel. So I'm going to be handing lots and lots of these things around the audience so you can have a look at them. So steel, there's a slightly different, slightly more complicated version of the 3D printing process that allows you to print in all kinds of different metals. So this is actually a steel-bronze composite. Here's another example. So this time, this is a hyperbolic paraboloid. Now, you could say, OK, well, we know how to thicken things up. We can just make a thickened surface here. I would argue that it's a better thing to do to actually sort of draw a grid on that surface, punch windows through the surface. And there's a number of reasons why you'd want to do that. So partly it's cheaper, right? You're not using as much material to make it. It's also, if you punch holes through the surface, it makes it sort of semi-transparent. So you can see through to the other side. It's not just a blank surface that's hard to appreciate what's going on. And also it allows you to say something about the parametrization of the surface. And so you're communicating more of the mathematics by having these holes here. So, well, why stop at the hyperbolic paraboloid? So this is a collection of quadric surfaces that I made for the Swinburne University of Technology in Melbourne, Australia. And these are the very large and very expensive versions. And next to it, you can see the much smaller versions, which is perhaps more useful. So I've actually used these. I was teaching Calculus 3 last semester, and I used these models to help the students understand what's going on. If you just give them the equation of these surfaces, it can be very difficult to figure out what it looks like and what the shape is. And with these physical models, you can, there it is. These are what the contours of the hyperbolic paraboloid look like. So I'll hand these around as well. You're going to be very busy. So far we've looked at really algebraic objects. So the geometry is given to you. You know what it is. The only issue is how to thicken it up to make it printable. And so I'm going to spend maybe the first half of the talk talking about if you have a topological object, what do you do? Right? You have a topologically defined object, and you need to give it some sort of geometric structure to give to the printer. Otherwise, it doesn't know what to do. Well, you might not have to choose the geometry. There is another way out, which is that you print something that's flexible. You just give up on I don't understand how to give this some sort of geometry, so I can print something flexible as well. But let's ignore that for the moment and just say we do want to give a geometry in Euclidean three-dimensional space to my topological object. What do I do? So there's I think maybe 3 or maybe 4 strategies that people use for doing this. And roughly, I've sort of grouped these into sort of the manual strategy. You know what the thing is supposed to look like topologically. You just want to draw something that works in whatever tools that you have at hand. And then there's the parametric or implicit strategy, which is where you have a topological description of this, but you also have a geometric description that you come up with somehow, either a parametrization or some sort of implicit description. And then there's sort of the iterative way of doing this, where you iterate, trying to improve trying to optimize some function to give you a geometry. So I'll just talk a little bit about these examples. So this is a cubic trefoil knot pendant by somebody called Vertigo Polka. So I've put this in the manual class. This is a little bit of a cheat, because in a way this is, so what has he done here? He's drawn this on a cubic lattice, and I believe that this may be the minimal cubic lattice version of a trefoil knot, and then he's sort of thickening these up. So in a way, this falls into the optimization class as well, but you had to choose things like the thicknesses of these pieces and so on. And now, so what about parametric? So here are some parametric trefoil knots, and of course, if you know that a trefoil is a torus knot, it's a knot drawn on the surface of a torus, then you can figure out how to parametrize this by using the coordinates on a torus. I'll just mention, so this is the, let's see, depending on your coordinate system, this is either the 2-3 or the 3-2 trefoil. And this guy here is the other one. And the difference between these two, well, the difference that interests me about these, this thing has what's known as a tritangent plane. So what that means is that there's a plane that is tangent to the knot in 3 different places, and you can see it here. This is the ground. And so if you have a knot which has a tritangent plane, then it sits stably on that plane. This knot doesn't have a tritangent plane, and this means that it only ever has 2 points in contact at the same time. And the consequence of this for a physical object is that it rolls, because it doesn't get stuck anywhere. So this, as far as I know, there were a couple of papers in the 90s about knots without tritangent planes, but I'd be very interested if anybody knows of any other knots that have no tritangent planes, so that I could 3D print a rolling version of them. But as far as I know, nobody's looked into them since. Okay, so now what about iterative trefoils? So how do you, what's another way of producing the geometry of a trefoil? So this is from the program NotPlot by Robert Schreien. And so the way that this works, how do you produce this geometry? So there are all of these little nodes which are connected by edges, and the edges must be always the same length as each other, but then you sort of iteratively shape the thing, and the nodes try and get away from each other and try and minimize some energy so they're trying to reduce how close they are to all of the other nodes that are not their neighbors. Here's another example. This is, so these are minimal rope length knots. So this is a minimal rope length knot. This is calculated by Jason Cantarella. So it's a little easier maybe to see. So this is the sort of full thickness version. So what this is you've got a rope. It's got some given radius, say radius 1, to the actual physical rope, and it's not allowed to intersect itself in any way. And then the question is, what is the minimal rope length? How tight can you tie the knot? And then this guy here is just the same position, but we just reduced the radius by a factor of 2, just to make it easier to see what's going on. And again, as far as I know, there's very few sort of known optimal results in this area. These are calculated by some, I'm sure, very fancy iterative algorithms that I'm not familiar with. But he has lists of all of the knots up to however many crossings you want online, and you can get these 3D objects, and then you can print them and see what they look like. And I just thought I'd put this slide in. This is Laura Tallman, has been doing a lot of work in 3D printing things. These are just an enormous collection of all kinds of different versions of the trefoil showing different aspects to its geometry. So down here is the minimal stick length of the trefoil. So how many straight line stick segments do you need to put together to produce the trefoil? And the answer apparently is 1, 2, 3, 4, 5, 6. So there are some aesthetic choices here, right? I mean, in a sense, this isn't mathematics. You just have to make some choices. But I guess I'm going to argue for a particular way that we should make choices. How should we choose the geometrical representation of a topological object? And so these are, I think, are the principles that we should do. So you should make as few choices as possible, and you should be as faithful as possible. And by faithful, I mean faithful either to the geometry the symmetry of the object. So if the topological object has symmetries, then you should, the geometric representation of those, of the object should also have those symmetries. And so really, I'm arguing for parametric being the way to go if you can. If you can find a canonical geometric structure on a topological object, then that's what you should be using. And it's telling you something more about the object. And there's something sort of new here with 3D printing over other ways that people have used mathematical visualization in the past. So what does a canonical geometric structure do? It gives you a very clean path from the mathematics to a computer model. You just implement whatever the geometric structure is. But then with 3D printing, we can continue that path. We can then produce a physical object that is very precise and faithful to the mathematics as well. And this is different if you're trying to carve something out of clay where you don't have that much control. You have to make a lot of choices in how you're producing an object, just because it's very difficult to physically produce objects like this. And there are some counter examples to that statement as well. The beautiful plaster models of algebraic surfaces from the 1900s. Who knows how they did those, but with 3D printing, it's a lot easier to do. So I was going to talk about a few examples of this. So here's an example of a kind of topological object that has been very popular in the 3D printing community. People like to make these structures that are sort of, I guess I'm calling them Mobius ladders. You have these Mobius strips which wrap around each other with sort of ladder structure, and then they self-intersect. And these are all examples of that. But what's going on with their geometry? How have they done this? This is some sort of combination of parametric, perhaps to start with, and then iterating to produce the surfaces themselves. So they have these sort of blobby kind of shapes, which are the hallmark, I think, of iterating to reduce energy or smooth out or something like this. And, well, this is our solution. So I should mention, so much of the work here is joint with Saul Schleimer, who's at the University of Warwick. So this is our version of the Mobius ladders, and I want to argue that it's better. So why is it better? So I said you should make few choices, and I also said that you should, as much as possible, be faithful to the structure. So what's going on with this? Well, so in our version, the rungs meet the poles of the ladder very cleanly, and they meet them always at right angles. And everything's sort of very flat. And there was a reason for this, and the reason is that we understand what the geometric structure of a Mobius strip is. A Mobius strip is flat. It has flat Euclidean geometry, and, well, unfortunately in Euclidean 3-space, you can't exactly do this. The way you can do this is in the 3-sphere, the unit sphere in 4-dimensional space. And so here's a parametrization of the Mobius strip in the 3-sphere, and if you like, you can figure out and see that each point of this is indeed radius 1 from the origin. And what's the point? So if you look at the derivatives in the theta and the tau direction, theta is going along the rungs and tau is going along the ladders. It turns out that those are at right angles to each other. And indeed, so how do you get from the 3-sphere to 3-dimensional space? What you do is that you stereographically project these objects from the 3-sphere to R3. And stereographic projection is conformal, and so that means that after you project, we also get all of these beautiful right angles. So what we're doing is we're saying the Mobius strip has a canonical geometric structure, and we're realizing it in, I would argue, the most canonical way you can hope to do, given that you have to eventually end up in R3. And I mentioned stereographic projection just because these are so beautiful. These are photographs of 3D printed objects. This is a demonstration of stereographic projection from S2 to R2. So the previous one was from S3 to R3. But this is the usual sphere sitting in 3-dimensional space. And then, so in fact, I can demonstrate this here. I don't know if you'll be able to see this very well, but so here's this, this grid that's been projected back up onto the sphere. And if I put the light in exactly the right place, then I get the grid projected down onto the plane. So I don't know if you can see that well. If you can, it looks very much like this one up here. The side of the podium, over here. Should I try that real quick? Shall I go in the shadows? Oh, the wall. Oh, that's a great idea. All right, let's do that. All right, let's see if I can do this without my hand getting in the way. So let's see. Something like that. And you can tell if I'm doing it wrong because I don't get right angles. About, well, something like that. You'll get the idea. Anyway, okay, moving on. So here's another example of a topological object that is difficult to get a geometric representation. So a Siphon surface is, if you're not familiar, a Siphon surface is a surface whose boundary is a given knot or link. In this case, the boundary is a link. There are 3 loops. There's a yellow loop, and a red loop, and a blue loop. And then the surface bounds the boundary of the surface are those loops. And so this is from a program called Cypherview by Jacques van Wilk. This is an animation of it sort of just relaxing this structure. So it starts off with a very, if I just go back and forward, so it starts off with a braid representation of the link in this case. So you have, so the braid is sort of wrapped around a cylinder this way, and so you've got a red, a yellow, and a blue strand, and then when we just go around this arc here, the yellow and the blue strands switch over, and it puts in the piece of surface to get that to match up. And then you relax it to give a nicer looking picture. And again, this is an energy minimizing iteration method to do this. This is our version of the same object. This is the Siphon surface for the 3-3 torus knot, torus link. I'll hand this around as well. And I won't say much about the parametrization. There's some very fancy mathematics that goes into this, which I don't fully understand. Saul, my collaborator on this, did a lot of the heavy lifting. I'll just mention the words fractional automorphic forms and Milnor fibrations, and that's about as much as I know about it. Well, I can show you a few pictures. So this thing is made up of patches. There are 18 copies of this fundamental domain shape here. This is a tiling of that fundamental domain out into H2. And so, again, this is all of the fancy stuff which produces the map from H2 onto the surface in S3, which, again, gets stereographically projected. And I'll just mention this pattern of triangles here. Again, we wanted to punch holes in the thing so that you can see through it, so it doesn't cost as much. And there's a problem with drawing patterns in H2 is that there aren't very natural patterns in H2 because you don't have any sort of scaling invariance, so grid structures don't really work. So we had to make something up. So this fundamental domain gets mapped onto by, this is the disk, so there's a conformal map from the disk to that fundamental domain in H2, which is calculated using Schwarz-Christoffel. And then there's another application of Schwarz-Christoffel from the Euclidean triangle onto that disk, which produces the eventual surface. So let me just compare the two. This is what you get, the iterative method. This is our fancy parametric method. Hopefully you can see that they're the same object. Here's a view along the two-fold rotational axis, the three-fold rotational axis. Here's a different view of the two-fold rotational axis. Here's the one that I think really shows the difference. So notice this red loop here. So we're viewing it face on. This is planar, but it's not circular, whereas our guy is precisely circular. And of course, Jack's version doesn't know that it's supposed to be circular, but we do because we parameterize the thing. So you can get, as I say, a more sort of faithful version of it if you know more about the mathematics, which is fair enough. And of course, sometimes your fancy parameterization doesn't work. So for example, the Borromean rings, we can't do this. So our parameterization only works for torus knots and links. But this iterative method, you can just do whatever you want. Any knot you want, you can write down a braid representation and use it to create a mesh and a 3D print. So this print was generated by Bathsheba Grossman. She's a mathematical artist who's really been at the forefront of mathematical 3D printing, and she used Cypherview to produce this model. Okay, one more example. So this is a little different. We're not saying how do you produce a good picture of a topological object. I'm saying how do you produce a good picture of an object that has too many dimensions. In this case, the hypercube is a four-dimensional polytope, and how do you produce a picture of it in 3 dimensions? So here, just to explain it, we're doing the same question down from 3 dimensions to 2 dimensions. If you have a flatlander friend of yours who lives in the plane and you want to show her a picture of a cube, what do? This is one of the things you can do. You can shine a light, and this is orthogonal projection of the cube down onto the plane. So if you do this, the same sort of thing from 3 dimensions down to, from 4 dimensions to 3 dimensions, then you get this kind of structure. Again, this is by Bathsheba-Grossman. Now, again, of course, I'm going to say that we're doing it better, so let me say why this is maybe not as good a representation as you could get. And let me just step back here. So you notice that there are 2 edges that appear to intersect. And to the flatlander, the 2-dimensional person, this looks like these edges are intersecting. And of course, that's not true on the cube, the true cube in 3 dimensions. Here, it's a little better. There are no edges that are actually intersecting, but there's an edge that passes through a face. And this doesn't happen on the true 4-dimensional object, and so you could argue this is less faithful, perhaps. Here's another way you can do it. You can do a perspective projection of the cube onto the plane. So this one isn't any better. You've still got intersections, but if you put the light directly above the face of the cube, then you get something that looks better. So here we've got no intersection between the edges, and the 4-dimensional version of this also has no intersections between the edges and the faces. However, this is still not perfect, and so to explain this, let me just go back to here. Where are the 6 faces? So there's a face down here, that's the bottom face. There are 4 faces here, these are the side faces, but the 6th face covers all of the other 5. So this is still not one-to-one. This is still, faces are colliding with each other, and here that's still true. There are 7 cubical faces, 1 in the middle and 6 around it, but the 8th cubical face covers all of the other 7. So how can we make a way to do this that is truly one-to-one? Again, we're going to use stereographic projection. But to explain this, let's start. So here's a cube. Again, we're going from 3 dimensions to 2 dimensions. Here's a cube inside of a sphere, and the idea here, this isn't a very good picture, is that the light rays project the cube outwards onto the sphere. So over here, I've got a cube inscribed inside of a sphere. I can project them outwards, the edges of this outwards onto the sphere to make a sort of beach ball sphere. And now I can stereographically project that, and this time we win. So where are the 6 faces? There's the 1 in the middle, the 5 around here. The 6th face actually appears outside here. And so, again, the light is at the north pole of the sphere, and so this 6th face appears outside as well, because stereographic projection is a bijection from the sphere minus the north pole to the plane. There's another picture, and this is the, where is it? Too many 3D models. This is the same thing done with the Hypercube. You can't really see it so easily, so here's a computer-generated model of the same thing. Where are the 8 faces? There's the 1 in the middle, there's the 7 around it. The 8th face is really outside of the whole thing. One more aspect of this, when you're trying to make this as faithful as possible, here's another issue. So this is what I printed. You could also have done this. What is the difference between these 2 pictures? So what I did to make this one is I projected the edges, the 1-dimensional edges of the Hypercube all the way down to R3, and then I thickened in R3. And I claim that's not as good as thickening in S3 and then projecting those. And the reason is that it shows less of the symmetry, right? You've got distortion from stereographic projection. Really, all of these edges and faces are the same. But here, you see that the sort of ratio between the thickness of an edge and the distance across a face is approximately the same everywhere. Here we have a small face with small edges. Here we have a big face with big edges. Whereas over here, the inner cube looks different from the outer cube in a sort of local way. And again, that's because what we're doing is not strictly conformal. So this way retains more of the symmetry of the true Hypercube in 4 dimensions than this version. So once you've done the Hypercube, you can do all of the other 4-dimensional polytopes in the same way. Let me just mention, so this is half of a 120 cell. So 120 cell is a 4-dimensional polytope with 120 dodecahedral faces. This is only half of it. It's cut off along the equatorial 2-sphere, because otherwise it would be very, very big and expensive to print. And Saul and I used this object to design a set of puzzles I won't go into the details of this, but these are sort of, we call these ribs. These are chains of dodecahedra from the projection of the 120 cell, and then these can be combined together to form these sort of Burr puzzles. Some of these are based on something called the combinatorial Hopf vibration, which is a structure on the 120 cell, which comes from the 3-sphere, and some of these we don't know really where they come from, but they appear to work and exist. One more project involving stereographic projections. This is called More Fun Than a Hypercube of Monkeys. So this is an example of showing particular kinds of symmetries. There are many objects, sculptures and so on, that show various kinds of three-dimensional symmetries. As far as we know, nobody has yet produced an object that has symmetry group, the quaternion group. So this is 1 ijk minus 1 minus I minus j minus k. This group is not a subgroup of the symmetries of Euclidean three-dimensional space, so you can't just make an ordinary object that works. Instead, it is naturally a symmetry group of, it's naturally a subgroup of the isometries of S3, and so again, we play the same game to make this, and you can't animate the three-dimensional object once it's printed, but you can still show the picture, the animation of what it looks like rotating around, and this is illustrating the symmetry. After just a quarter turn along this, these monkeys get back to the original positions. Okay, so now I'll move on to talking about some other projects I've worked on, not really so much thinking about the topological ideas, but still with some interesting mathematical and computational problems. So Marco Marlo is an artist. He works with mobiles. He generally builds them out of, metal, cutting them out of sheet metal and bending wires and so on. And we got talking about 3D printing mobiles in place. And so there's a little bit of interesting mathematics here. If you're designing something like this on a computer, then you can use the fact that you can calculate volume centroids to balance the mobile perfectly. So rather than having to sit there bending things very carefully and rebalancing and so on, you can just calculate so how do you build this? Suppose you've built up to here, you take all of this thing here, you calculate the volume centroid, and that tells you where to put the next hook so that it will balance perfectly. And this is a question that I've thought about, didn't really get anywhere. Maybe somebody here will find a way to do this. So presumably most of you have seen the old question of how far out can you push a stack of dominoes. And so this last domino is pushed out so that it's balancing just on the edge of the next domino down. And then these two dominoes, their center of mass is just right above the edge of this next domino down here. And you end up with the harmonic series. So the question is, how far can you push these out? Well, you can push them out infinitely far if you have an infinitely tall stack of dominoes, because you can just keep pushing. So why am I talking about this? Well, this is the same thing as this upside down. It's the same problem. And so the question I was interested in is, if you're not just using uniform dominoes, if you're allowed to change the length of these things and the thickness of them, how far out can you get? Can you produce a mobile, this sort of linear mobile which doesn't have any branching, that goes an unusual length out here? So I didn't really get anywhere with this, but maybe there's some interesting mathematics and interesting things to be solved there. Here's another project, again, with Marco. So these are mobiles that are trees. So this is a binary tree over here. This is a ternary tree. So I don't have a photograph of this, but if you look at the bottom of this, you get the Sierpinski triangle. And this is a quaternary tree. And so the interest here, this is a picture of the bottom of the quaternary tree. And it turns out there's a lot of pieces in this mobile, which is good for 3D printing because you wouldn't want to make it by hand. And so here we really have the problem of thickening up a graph, thickening up a one-dimensional object. Because we've got all of these pieces, we need an efficient way to do this, partly so that working with the model is convenient. And also, at least the service that I use for 3D printing these things has a limit of the number of polygons in the mesh. So you can't go above 1 million polygons. And if you've got 1,000 pieces, that's not many polygons per piece. So how do you thicken these up? The obvious thing you might think about is, well, just put a sphere around each vertex and put a cylinder around each edge. And the problem is that Boolean operations on these don't work reliably. So this is one of the banes of my existence, is the fact that mesh Boolean operations fail an incredible amount of the time. And somebody needs to fix this. But so how else can you do this? You need to produce a mesh that gives a neighborhood of a graph, and you need to do it efficiently, and it needs to not break. So there's a couple of ways I thought about this. I'll just tell you, it's quite a simple idea, but I think it's interesting. And I think George Hart is the first person who actually wrote this down. Here's a two-dimensional picture. I've got 3 edges coming into a vertex. I need to thicken this up. So this is sort of schematically, I draw polygons around those edges. I move them in until they touch. And then I've got a polygon here, and then I've got another polygon at the other end of this edge. I produce some geometry around this edge just by taking the convex hull of this polygon and the polygon at the other end of the edge. And I, again, put a convex hull around the remaining geometry near the vertex, and then I've got my neighborhood. Here it is in 3 dimensions. So this is the corner of a tetrahedron, and this is a loop that's hanging off of that tetrahedron. So here are the polygons that are moved in as close as you can to the vertex so that they don't crash into each other. There's the convex hull around this polygon and the polygon at the other end. And here's the convex hull around everything else. And then you just stitch those two together, and you get your neighborhood. So this is a pretty efficient way to do it. I'd be interested to know if there are other ways to do this efficiently. So here's another project. This is, again, joint work with Saul Schleimer. This was a difficult engineering project to get 3 gears that gear into each other. You can turn all 3 together, but you cannot turn just one on its own. So how do we get into this? So once you've noticed this, you can't stop seeing it. This graphic design feature of 3 gears that are pairwise meshing. I particularly like this, making the city work together. It's classic, council bureaucracy. Here it is again as a cooperative learning logo from the University of Saskatchewan. So 3 pairwise meshing gears are usually frozen. You can't move them. So here's a challenge: find a triple of pairwise meshing gears that does move. And so this is one example of that. So I'll say a little bit about how we got into this. So there's a couple of configurations with 2 linked gears that inspired us. This is umbilic rolling link by Hellerman Ferguson and knotted gear by Oscar van der Venter. These both consist of 2 solid tori with sort of gearing of some sort around on the outside. So this one, there's a 3-2 trefoil and a 2-3 trefoil, and if you move one, it must twist around the other. You have to move them both together. So you can, another way to think about this is if you imagine a nut on a bolt, but then you curve the bolt around to be circular. And so this is how they sort of interact with each other. So they have 2 gears. We wanted to do the same thing with 3. And so how did we do this? So we chose the 3-component Hopf link as the basis of the design. So this is, well, here's a picture of it. Each pair of rings is linked with each other. Incidentally, we had to use this link rather than the Borromean rings as what people always think it should be. It turns out the Borromean rings cannot be made with circles. And they need to be circles so that you can turn them into gears because you need them to rotate. So again, this wouldn't be a problem if you were doing this thing topologically or in some other space, but R3, you don't have any options. So the first thing we did is we sort of found maximal positions for these rings. And so we just sort of inflate all of the rings at once, fixing the 3-fold rotational symmetry until they bump into each other and you find the maximal thickness. And this already is sort of annoying computationally because so it turns out there's no closed form solution for the distance between 2 circles in R3, which would have been really useful when we're trying to maximize how to do this. So this was done numerically. And then, so we printed out here's a test version of just those rings. And we were hoping that it would just stay in that configuration, that it wouldn't be able to move out of that configuration. And the intuition here is, so if you could move this out of the configuration of these 3 rings like this, then if you could jiggle it around a little bit, then that would say to you, well, you don't have the maximal thickness of these tori. And so it turns out that if you break the 3-fold rotational symmetry, then you can move them out of place. So we don't want this configuration. So to make sure that this doesn't happen, we design the gear teeth, which both keep it in place and mean that the three rings have to rotate together. So how do we design the gear teeth? So let's look at how these three rings touch each other. Let's take away one of them just so we can see what's going on. These two rings touch in two places that I've marked with these two red spheres. I'll just tilt it up so you can see what's going on. This is a symmetrical configuration between these two rings. Tilt it back down again. And as you rotate this ring around this one, these longitudes here trace out the points of contact. And so these are the places that have to have gear teeth if this is going to work. Let's put in the third ring again. So now there are 4 longitudes around this torus which need to have gear teeth on them. So I'll take these inner two longitudes and put them on this one here. And then what we have to do is figure out how to draw gears on this blue longitude here that mesh with this red one. And so there's a slight annoyance here. There are these 2 longitudes on the inside of this torus here that are very close to each other. And so if you put gear teeth on one of these longitudes, then it will interfere with gear teeth coming that are supposed to mesh with the other longitude. And so what we decided to do was just treat these two as a single gear chain, which we determined just using, so we just chose something. It turns out this is toroidal coordinates here. So then the question is, what should the gear teeth look like on the other ring here? We actually looked into, so this is a current area of research. There are people investigating what should the shape of gear teeth be in 3 dimensions. The 2-dimensional case was worked out by Euler in the 1700s, but the 3-dimensional case is still open. We even went so far as to implement some of these things before finding out that none of them will actually work for our case. So what do we do instead? So we have these sort of, we've decided on these gear teeth, and the idea is this. We know how these 2 rings are supposed to rotate relative to each other. And so the idea is, let's imagine that we've made this gear teeth, these gear teeth on this ring, but that this ring is made out of clay. And then we're going to move both of them forwards and see what shape these teeth carve out of the other ring down here, and use that shape as the gear teeth on the other piece. And so this is what we do. So here's a copy of this curve here, just moved out a little bit. And these are the images of that curve under the combined motion of the 2, seen relative to this ring down here. So what's going on here, so whatever the shape of our gear tooth on this ring down here is, it can't have any pieces up here. Because if it did, then it would crash into the blue gear teeth as they rotate. However, I can have parts of the gear that are underneath all of these things. So if I have a shape of a gear down here, then it will closely track this edge of the gear up here. And so that's what we do. We take this curve down here from that construction. We do the same thing with the curve up here and the curve down here. We join them up, and we have a gear tooth, the shape of a gear tooth. And rotate them around by the symmetries, and this is what you get. And after we did all of that work, we found there were easier solutions. So this is just 3 screw gears that are arranged in the right way, so that, again, they're pairwise meshing, but they all move. And here's a linear version, right? So the previous 2 have been sort of rotational versions of this question. This is a linear version of the same idea. And I think there's lots of other places you could go with this. I'd love to see some more solutions to this question of 3 gears that are pairwise meshing, and yet they can move. So another project, this is joint work with Jeffrey Irving. There wasn't a huge amount of new mathematics here. But let me just say what this is. So this is the construction of a fractal curve. So in this case, this is the Terdragon curve. And you start with a straight line, and then you sort of make it more crinkly by somewhere further down here, there's a zigzag like this, and then even further down it gets more crinkles, and you keep going. And this is just replacing the sort of time component of that process with a space component and producing this. And so, I mean, the problems here are sort of thickening and smoothing. In particular, some of the curves that we're interested in doing have self-intersections. We don't want that. So we need to smooth out those curves and thicken them up in a natural way to see what we get. So here's a few examples of this. So this is, again, this is the Ter-Dragon curve. This is the Hilbert curve. So you can really see the, where are we? Here we are. So you can see that this is, I believe, the fourth stage of the Hilbert curve, starting with just 3 edges of a square. This is the Sierpinski arrowhead curve. Once you see the faces here all over this, you can never unsee them, so I'm just going to tell you about them right now. And this is the dragon curve. And so Jeffrey and I thought about this quite differently. I was sort of parameterizing it directly. Jeffrey's method was to start with a very simple mesh and then smooth it. He used a loop subdivision to do his smoothing. And it has an advantage so there's a self-similarity to the fractal curves, which comes through in his case in the smoothed out version of this. So this guy is colored according to self-similarity of the patches of the surface itself. So all of these pink pieces here are all self-similar with each other, and you can really see how this works. And there's some sort of complicated relationship between how the boundary of the surface interacts with the smoothing algorithm that determines where these patches of actual geometric self-similarity occur. Okay, last, I think I've got time. Last project, again with Jeffrey Irving. So these are hinged negatively curved surfaces. They look a little like doilies, except you cannot lay them flat. It doesn't work. This is printed in one object. So we did not print out hundreds of tiny little triangles and then somehow glue them together. It just came out of the printer like this. Here's another view. So it's maybe a little easier to understand, well, what is going on here. So here I've got a vertex with 7 triangles around it, and here I've got a vertex with 6 triangles around it. So what's going on here? Let's look at this example first. That's this one. So this is this has equilateral triangles and 7 equilateral triangles around each vertex. Of course, if you do 6 triangles around each vertex, then you get just the equilateral triangle tiling of the plane. But if you do 7, then you have too much of it. And so, in a sense, this is a model of hyperbolic space. So how do we get from this? Well, what's the problem with this version? Is it's sort of there's a lot of angle defect at each vertex, and it makes it sort of not very smooth. And so what we did is each triangle here, you subdivide into 4 triangles to produce this object here. So this is the same thing as how do you make a geodesic dome? You start with, say, an icosahedron, which has 5 equilateral triangles around each vertex. You subdivide each triangle, say, into 4 triangles. You get extra vertices at the midpoints of the edges, and you move them out onto the sphere. And this gives you a smoother version of the, smoother approximation of the sphere. And this is the same thing, but going from the other direction with negative curvature rather than positive. And so, well, the question is, how do we do this? So this goes all the way back to some of the things I was saying at the start. This is a flexible model. We're not giving a true geometric structure of what this, the hyperbolic plane inside of R3. But at the same time, you have to give something to the computer. Right? I have to arrange these in space so that they don't crash into each other, and how do you do this? There is no canonical geometric way to do this, so instead what we do is we use the iterative method and simulate. So we start out with a triangulation in the Poincaré disk model with a few sort of small noise things added to this just so that it's got somewhere to start from, and then we put springs on all of the edges and make them shrink and try and get all of the edges to be the same length. And then if we go to so then the last slide of this is where all of the edges are the same length to whatever precision you want. So this is the last slide. And then we just put our triangular pieces, one on each face of the triangle, and then we're done. So, so here are some references for some of the different projects that I've talked about here. You can ask me later for these, and that's my talk. Thanks very much.
we have time for some questions or comments or?
Yeah, how difficult the hyperbolic surface? How difficult is it to get the 3D printer to lock one triangle around the next triangle without having the plastic glue together?
So you need right. So Shapeways, the company that I use, recommends a tolerance of 0.5 millimeters between two pieces that are not supposed to be glued to each other. So you just make hinges where they have that much gap, and then it works. And then somebody at some point hoovered out all of the unused material from inside of all of those hinges, but it wasn't me. So I don't know how difficult that part was.
There's a very nice embedding of the sphere as a double cover of the projected plane, which is involved in the problem of turning a sphere inside out smoothly. Have you seen models of the around the middle stages where you've got a nice double cover?
I've seen clay models of this sort of thing. I haven't seen anybody 3D print it. Yeah, I mean that would be an interesting project to print the stages of them and maybe have build a very large zoetrope so that you could have them spinning around and you would animate and you would see in 3 dimensions how it works. But no, I haven't seen anybody try and do that. It's a good project. I don't know if there are. Do you know if there are sort of parametrized versions of those stages in between?
Well, I would think it probably work because there's a movie.
Right.
Imagine doing the movie frame by frame.
Yes. So yeah, no. So likely you would be able to take that data and without too much trouble produce models. Yeah.
When you showed how you thicken the 3-dimensional graph, you started with some polygons.
Right.
What were these polygons?
Let's see. You mean here we go. So you mean these lines here?
No, but then you drew blue polygons.
Oh, these ones here.
Yes. What are these polygons?
So this is so take these edges here coming from these polygons around the edges and just take the convex hull. And delete any triangles of that all come from the same octagon. Does that answer your question?
Does arbitrarily choose octagons or?
Well, so you choose octagon. Well, you need to choose something and choose something so that it's round enough and it's few polygons enough and get it to work. Yeah. Yeah. So not so canonical, but it works.
Okay, so on behalf of the conference, I'll have the chair of the local organization, Professor Thickening, to present a souvenir to Professor Henry's.
Right, good. So thanks for very nice talk.
Thank you.